think we're back. We've got a couple of things to do today. We got to talk about numbering systems. So the base 10 system that you know, counting from 0 to 9 and then adding more numbers until you get to however far you want to count. The binary system is a big one that we need to talk about just because a lot of data is going to be stored using the binary system. We're going to talk about just numbering systems in general also, so that you're not stuck to any particular base, although there's not a reason really to create your own base system right now. We're going to look at character encoding. So how do you represent letters and words if all you have are numbers in a computer? So we'll look at that. We're not very long in depth at all on that thing, but just the idea of how you do it. And then unit standards. So we've talked about measuring a little bit. We did some measuring with a different multimeter. I brought out this multimeter today just because, well, we'll get to it in a second. But how do we know that that is accurate? And so there are these standards out there that exist. And so we'll talk through those a little bit. I'm not going to go into detail about how each standard is created, maybe some of the interesting points of how they've evolved over the years. I do have our new thing for today is a set of gauge blocks. And so we'll look at how those work. Let's start with kind of where I don't know if we left off here yesterday or Tuesday, but we sort of did. We had a little circuit, and we actually had this multimeter over here. We actually had this one. Now there were a couple of things that we were having trouble with. One was measuring current. Everything else was fine, measuring resistance and all of that. There were some things we had to remember as far as when you're measuring resistance in a circuit that's built or constructed, that it's going to probably give you the equivalent resistance of point to point, not the resistance of an individual element at that point, at those 2 points, because there might be multiple elements connected to that point. And so that was one thing. Also, if the power was on the circuit, we weren't going to be able to get a good resistance measurement either. Then we tried to measure current, and I did, well, one thing wrong for sure. Another thing kind of wrong. You'll notice that now there's a little blue light LED in here that wasn't in there the last time we looked at it. And then one thing that was just broken. So one thing I did wrong was when we were measuring, I never switched the leads from this side over to the side to measure current. So if you'll notice on this multimeter, it has V for volts, ohms, the continuity, diode, capacitor type test, all on this side, but current is over here. So if I want to measure current, I have to actually, for this multimeter and for a lot of multimeters, I have to remove it and put it over here. And I never did that, so we weren't going to be able to measure current anyway. Another problem was that I didn't have anything that was really drawing any current. I remember I said that we just made a little resistor network, and it was just a really, really bad heater is all it was. But it was the resistance values we have here, like these are all 1,000 ohm resistors, I believe. And so it was pretty high resistance, and so it wasn't really drawing current that this multimeter would have been able to read very well anyway. It might have, but it would have been a very tiny current. So I've added the LED to have something to draw current. So we have to do some work now a little bit and light up a LED. The third thing that was just kind of out of our control was we did open this one up and look inside at the fuse. It has one of those large bus fuses in it. At the time, I didn't have a way to check if that was good or not. So I went and found one of the cheap multimeters that I have. And turns out that fuse was blown. So I ordered a new one. We'll replace that sometime once it gets here. I don't know how long it'll take to get here. But that we wouldn't have been able to measure any kind of current at all because the multimeter itself was blown. I did find a couple of my leads that have the spring clips. These are really handy. So they have little clips on the end where you can clip them to different points. This set also has some other things that are kind of handy, not that we'll use them that much, but they're handy if you use them. And the whole set of these leads was $15 maybe, I don't remember. But it wasn't like they were super expensive. Here it also comes with this. Now this one, the leads are built into this device. So what this one's for is if you want to, maybe there's a surface mount resistor right here and you want to measure on either side of that. It's really hard to get two traditional leads like these guys in there. So this one lets you just, you can hold it like that and measure. Well, actually that's a capacitor. There's another resistor. I could measure resistance values. Now again, I'm measuring them on the board, so I might not get the resistance of that particular thing. I'm going to get the equivalent resistance at that point. But this little tool is kind of handy if you're using a lot of surface mount things that you're trying to measure the board itself. I don't think we're going to need that for this class. I just wanted to show it that there are different types of leads out there, and they're not terribly expensive, and most of them are interchangeable. Most have the same type of plugs in here that you can, I'll get that connected. You can use on a different variety of multimeters. They're not universally interchangeable as far as I know. Nothing is, but at least they're close. This is the kind of multimeter I was talking about that is not self-ranging. So remember, this one doesn't have that many options to choose from, where this one has all kinds of options to choose from. And so this one, much cheaper multimeter than the Fluke over there. This one, it's $8 or something. I don't know. It may not even been that much. It works in a lot of the same way, but it doesn't self-range. So, and actually, look, there's a separate plug over here. I have a 20 amp side. I have measuring regular amounts of current, and then I have measuring the resistance and voltage over here. And let's see if we if we were trying to measure the resistance of this guy. In fact, let's see if our spring clamps will fit in this multimeter. I haven't ever tried them in this one, but it would be nice if they would. So let's see. So you can see how they work. Let's see. Here's the red. We want to measure. Yeah, they'll go in there, even though it has a little bit different setup. All right, let's get those out of the way. Let's put the other end in here. Now you'll notice these actually have a pass-through where you can plug another set of leads in on top of these if you wanted to for some reason. All right, so let's just clamp these on. This should be a, well, let's turn it on first. So this one actually has a on button, and the resistance measurements are up here at the top, and you'll see, well, here's the continuity checker built into here. It probably sounds really bad if it sounds at all. It's okay. And then do I want to measure something in the 200 or less ohm range, the 2000 or less, the 20,000? So the goal is you need to know something about what you're trying to measure with one of these. So if I tried 200 and this is a 1,000 ohm resistor, let's see what happens. It just gives me 1. So I know this isn't a 1 ohm resistor. So something, usually whenever you get a 1 or a 0 or something, a 0L or something like that, there's over the limit or whatever. This one just displays a 1 whenever it's over the limit. So let's switch it over to the 2K side. So 2,000 ohms is larger than 1,000 ohms. That one should work for us. And it does. We get 0.986, but we're in the, this one doesn't give us units on it that I can see. There's no units on there. So you kind of have to have an idea of what the units you're dealing with are. So these would be thousands of ohms. So, well, 1,000 ohms, but I've got 0.986, so I've got 986 ohms. If I switch it over to the 20,000, notice I just get fewer decimals. So it's expecting something to have to report a 10 over here or even a 20 something, and then I get fewer decimals and so forth. It basically, you want to select the range. You don't want to just go to 20 million every time. This one reads 0 when it's at 20 million. So you want to read the one that's larger than the resistor that you have, or voltage or current or whatever it is you're doing, but only the next largest one. So 2,000 is the one that's larger than the 1,000, but not 20,000 or 200,000 or 2 million or 20 million. you want to get as close to this value as you can. Now, if you don't know this value, you can do what I did, where you just kind of scroll through them until you find one that doesn't give you an error like that. All right, let's put this one back and let's see if we can do a current measurement, since we didn't get to do that last time. So we'll worry about how to put them in the breadboard later. We're not going to build anything on a breadboard just yet. All right, so current measurements are over here, and there are two of them. There's the one with the sine wave symbol. Let's zoom in a little. Let's see, that's this button. So we can get all of this. Yeah, there's the ones with the sine wave symbol. So this little line that's curled, and then there's the one with the straight lines on it, the straight and the dotted line. Remember, the sine wave is alternating current. We're going to, actually, I don't have this connected to any kind of power yet. Let's plug it into DC power. So I've got the purple one as positive, and the black one is negative. We'll turn it, it's not turned on right now, so nothing's going to happen yet. And then we got the same idea over here, where am I trying to measure 200 microamps, 2 amps, 20 amps? If I'm on the 20 amp one, I do have to switch over to this plug over here. Actually, I almost made the same mistake again. I do have to switch to this side to measure current. And let's go for the 20 milliamps. Let's see what we're at. All right, so to do that, notice nothing's actually happening yet. When you measure current, you do not want to measure across an element, because basically what that does is it puts your multimeter in parallel with the thing. And if you remember your Kirchhoff's current law and voltage law and the things about how current flows in a circuit, when you put it in parallel, it will split that current. Some of the current will go to your multimeter and some will go to the element that you're trying to measure. And your multimeter, when it's measuring current, has a very low resistance, so it will take a lot of the current, and that's usually how you blow the fuse that's inside the multimeter. Instead, what you want to do is put it in series. So right now, I have a gap between this this resistor and this LED, and so I'm actually going to put the multimeter in that gap. So it is in series with these two elements. It's right between them, so it's going to measure the current leaving this resistor and going into that LED as soon as I turn it on. Now I've got the voltage set. Normally, I've got a power supply off to the side over here, so you can't see it. So you turn those off, like the voltage that you want to supply. You turn that all the way off before you actually turn it on. Otherwise, there's a chance that you left it at some position where it's trying to supply 20 volts and you're just going to burn up your LED. So we'll gradually crank it up here until we get, getting nothing. Let's see. Oh, well, that's weird. Why'd I gotta check my little LED here. All right, that is I may have already blown it up actually. I think actually what I did though is I have it backwards on the power supply. All right, let's turn our voltage back down and see if that does any better. There we go. So LEDs, if you don't remember, they are biased where they're diodes. The D part in LED is a diode, and it only lets current flow in one direction, and I actually had it backwards. All right, so I'm applying 4.7 volts, across here, so 4.7 volts in the entire circuit. And now you can see, you can't see, I can see, there you can see, I've got 0.82 milliamps. That's not 0.82 milliamps. Let's put it on 2 amps so we get actually it is 0.82 milliamps. It's a really small current going through there. LEDs, this is one reason you use them as lighting, is they draw very low amounts of power, right? So very low amounts of current also. And, yep. Depending on the range, you get slightly different readings. but if we go to the microamps, we're above 200 microamps, so it's not going to read that one. 0.77 milliamps, somewhere there. So a very low current, but we can measure it. And so I just wanted to make sure that we knew how to do that. I'm not probably going to ask you to measure current very often, but you may need to. Measuring current is the one where you do it wrong and you're going to blow the fuse out on your multimeter. And they're not expensive. Well, the fuse for this one, they're like, I don't know, $5 or so. A fuse for like this multimeter is cents, 10 cents maybe. I don't know. You just have to find one is the problem. You usually can't buy a single fuse. All right. Moving on from that, and we're going to come back to lots of electronic type things as we move throughout the course. Obviously, we're going to use a lot of sensors, and they're going to be electronic sensors, and we will need to do a lot of more multimetering and building on the breadboard, things like that. But today, we'll get to our gauge blocks later. Let's talk about number systems just a little bit. And I have Python or Thani pulled up over here so that we can use it a little bit also. You don't need to necessarily, but there is, well, maybe there are two things I want to show you in there about how to deal with data in Python. So we'll kind of build that into our numbering system. So obviously, hopefully, we all know about the base 10 system. Oh, we need something darker than that. Let's find, there we go. Base 10 system. So that's where you have the numerals 0 through 9, those characters, and you create all your numbers from that. And I don't think I need to explain how to do that, other than it might become important if you're dealing with a measurement system to distinguish when you're in base 10 and when you're in base 2 binary system, because you might be having to move between both of those when you have numbers that you're familiar with and the numbers that the computer is having to deal with. And so to do that, to distinguish between if you're in base 10 or base 2 or whatever base you're in, let's say we have 1,234 and we want to show that that's in base 10. We put this little guy down here, so that just shows that we're in base 10, the decimal system. That we all know about. No tricks there. Then, like I said, a lot of times you're going to have to, you may not have to think or write or code or anything in the binary system, but you need to be familiar with it, because when we go to store data, there's a chance that it will be binary in nature and we might need to do something with it. So the difference between binary and base 10 is that binary is base 2. So there's only 2 digits. Instead of 0 through 9, you just have 0 and 1. Now in a computer, it doesn't literally have 0 and 1. It has high and low. So there's a high voltage somewhere and a low voltage somewhere on a chip. So it doesn't literally think in ones and zeros like you might think. A lot of times you'll see binary and it is a series of ones and zeros. But in the computer, it's a series of high states and low states. So this is base 2. So, this number is not 101. When I put the little subscript 2 in there, this number would need to be translated over to the decimal system to know its decimal number. So you would just have a series of zeros and ones. It works the same way that the base 10 or the way any number system works, where each one is a placeholder and each one represents progressively larger numbers, right? So we have the units place, the tens place, the hundreds place, and the thousands place in base 10. You have the same idea over here, except you have the one, or I don't know if you would call it the units place like you do over here, but the first position, 2 to the 0. So this number, there's two options here. It can be a 0 or 1. So your base is 2, and it's to the 0 power. So it can represent the number 0, our number, base 10 number 0, or 1. 2 to the 0 power is 1. This position can represent 2 to the first power. So it can either be 0 or 2. And then this number can represent 2 squared. So it can represent 0 if it's a 0, or it can represent 4. And then this number would be 2 to the third, so 0 or 8. And you can string different numbers of these would be called bits. So each position is a single bit. So you've heard of like an 8-bit machine or a 64-bit machine or whatever. These are the bits they're talking about, and they mean the number of consecutive bits that represent data. So if I just have an 8-bit machine, I have 8 of these strung together, and that's one piece of data that I can do something with. If I have a 64-bit machine, then I have 64 of these, and obviously that's going to represent or be able to represent a much larger number. So an easy way to maybe think about that, how that affects the performance, is if you've ever seen an 8-bit video game, it's pretty blocky, and it doesn't have as many colors in it as a modern day video game. Just think about the colors. If I have a bit or 8 bits strung together, then I could have, we could do the math here, 2 to the 8th, 256 different colors. If I have a 64-bit machine and I want to use one of those strings of 64 bits to represent colors, I don't even know if my calculator can do that. 2 to the 64th. Well, it does. 1.8 times 10 to the 19th different colors. So way different amount of colors I could use if I was thinking of the amount of colors that I could represent with a single 8 bits is a byte, so a single byte of data. Anyway, this same process works whether we're over here. So the idea over here would be, this would be base 10 to the 0. Here it would be 10 to the first, except I have 9 different values, well, 10 different values, because I could put a 0 in here. So I could have 4 times 10 to the 0, so I could have 4 times 1. I could represent a 4 here. Here I only have 2 options. I can be a 0 or 1. Another system that's common with computer systems is hexadecimal. Let's see, is it XI or XA? I never remember. Hexadecimal. So this is base, and if you look at the word, you have hex, which is normally 6, but it's not base 6. It's hexadecimal. So decimal is usually base 10. So hexadecimal, this is actually base 16. And it's useful in computer programming. It's not necessarily how the computers work, but a lot of the really low-level coding occurs in hexadecimal system, because you can use 2 positions, like 2 numbers or letters or whatever it might be, to represent a larger number when you have a base that's larger than base 2 or base 10 or whatever. I think it's the Babylonians, they had a base 60 system, so theirs was a very different system than what we have. So hexadecimal, it has a different set of units since it goes to 16, not units, but variables that you can put in all the spots here. So it uses 0 through 9. And then it doesn't use 10 here for the next spot. It uses A, and then B, C, D, E, and F. Right off the page. That's a B. So there's 16 different spots, or 16 different, not spots, 16 different values that can be in each spot. So you get numbers in hexadecimal that look like 1F, for instance. So it takes the 1 and an F. The F is in the 16 to the 0 spot, and this would be in the 16 to the 1 spot. So 1F, this number would be 31 is what that would represent. Pretty sure, 31. For if you're taking the course, we'll have some quizzes and exams where you'll need to convert maybe one system to another. So let's look at how you can convert. There's actually only 2 equations to convert any system to another system. And they're generic. That makes them generic, right? So that you can put any set of base into a system to convert to a decimal system. Because most of the time we want to either convert one of these base 2, base 16, or base 8, or maybe we want to create our own special base for some reason. We want to convert those over to decimal, or we want to convert decimal to that system. So I think I said it a little bit wrong. I said from any system to another system. There are equations to do that, but we want to mainly go from any system to decimal, or from decimal to another system. Yeah, on the calculator, a lot of calculators do. I'm looking at mine to see if it does. I've never actually tried. Let's see if I have a conversion thing that is obvious in here. I don't know on this particular calculator if there. I'm sure there is. I've never actually tried to do it, but yes, a lot of these conversions, particularly the common ones like binary and hexadecimal, probably are built-in functions in a calculator. There are certainly, you could create any kind of base system that wouldn't be in a calculator, but they probably are. I don't see them in this particular one, but I've never looked for it either. Let's go through the process of how base n should be well, I would certainly have to go through and find where base n is, but this calculator may not be set up for that. I don't know. It certainly would make sense that they're in there, though, to have a base n conversion. So how is it doing that conversion? Here's what it's doing. So if you want to go from an n base, or in my equation, we're going to use a b for the base. So b would be 10 if you're in decimal, or 2 if you're in binary, or 16 if you're in the hexadecimal system. So n, that's going to be our decimal number. So the 1,234 we want to get to, or whatever. N is going to equal, and it's a summation of n minus 1. So this lowercase n is the number of digits. So 4 digits, 2 digits, however many digits you have in the number you're trying to convert. We're going to start with the index of 0. That's going to correspond to this 0 that we had here, or here, or here. You want to start at the let's talk about this. Take a moment to talk about this position. Let's use it over here, though. This is the least significant bit, and the one that's the farthest on the right is going to be the most significant bit. What that means is how large of an effect does this position have on the number that this binary string represents, versus this one. How big of an effect does it have? So let's go to base 10, since we know that one. We're more familiar with that. It has the same idea. We just don't call these bits necessarily, but same idea. This one here represents 1,000. This 4 represents 4. So this 4 is the least significant bit. If we were calling each one of these positions a bit, this 4 would be the least significant one, because it only affects the number 4 out of 1,234. Whereas this 1 represents a 1,000 out of 1,234. So we have names for some of these. The most significant bit is the one on the left. Least significant bit is the one on the right. And we'll need that just to be able to talk about things. We don't necessarily need them for anything beyond that in this course. So least significant one is the one that has the least significant effect on the number you're creating. Most significant has the most significant effect on the number you're creating. All right. D sub I, I'll write these down in a second so that we can remember what all these different things represent. D sub I is the digit. So this digit or this digit or this digit or this digit or whichever one. And then times B, again, that's the base, raised to the I power. So I is the index. It's going to go from 0 to however many digits you have minus 1. You're going to have to subtract 1 off because we're starting at 0. We don't start counting at 1. So even though I have 1, 2, 3, 4 bits in this number, I'm starting with 0. So my index is going to start with 0, 1, 2, 3. So that's why I have to subtract 1 off of the n. So I is the index, n, lowercase n, is the number of digits. D sub I will be the individual digit. How do I want to call it? The digit value. So is it a 1 in this spot, or is it a 4 if we're doing in base 10? We'll do digit slash bit value. What else do we have in here? N, capital N. That's the decimal equivalent. B, so raised to the I power, I guess. B is the base system, so maybe we won't put the I in there. We already have I as the index. I guess I never wrote it down though. And I can use this equation no matter what base system I want to operate from to get to the decimal system. I can use any base system I want. I can use any number of digits, so I could have a 8-bit number up to a 128-bit number if I wanted to. The reason I want to show this is, one, to get an idea of how these systems work, but also I want to show how to code some things, right? So should we do this by hand first? Maybe we should do it by hand first and then we'll code it. There's a similar equation that we'll also use for doing the opposite, going for, well, it's an algorithm. I don't know if we call it an equation as much. But it's a process to get from decimal over to another base system. And we'll look at that too. But it's a little bit simpler actually. So let's go from, here, let's take a number, a binary number, 1, 0, 0, 1, 1, 0, 1, base 2. So this is a binary number, and we want to know what it represents in decimal system. So what is this number in decimal, base 10? And so what we would do here is we would try to complete the summation, or n equals the summation. There's 1, 2, 3, 4, 5, 6, 7. So lowercase n is 7 minus 1. So we're only going to count to 6 because we're going to start counting at 0. So that'll give us 0, 1, 2, 3, 4, 5, 6, which is the 6 in the numerator up here, or not the numerator, above the summation symbol. The individual digits are going to be 1, 0, 1, 1, 0, 0, 1. So I'll leave that as D sub I because they're going to change depending on what position we're in for that index. We're in base 2, so we'll leave 2. And then this I is also going to change based on the index, so I. So you start at the least significant bit. So this is really, if you're doing this by hand, this might be the only place that you would make a mistake, is starting over here and working your way across. And this equation would not generate the number you're trying to generate at that point. So you do start at the least significant bit. And you can kind of rationalize that because your index is going to be 0, and the first number that's going to pop out of here is 2 to the 0, which that's associated with the least significant bit. So you do have to be sure that you start on the least significant bit side. So that would be, I'm going to expand this summation now. So 1, di is 1, times 2 to the 0 is just going to be well, we'll write 2 to the 0, it'll be 1. And then it's a summation, so plus, we increase our index to 1. The next spot is 0 times 2 to the first power. And then we move over plus 1 times 2 squared plus 1 times 2 cubed plus 1 times 2 to the, oh no, that's a 0, 2 to the 4th. Now we're over here, we'll move down, plus 0 times 2 to the 5th plus 1 times 2 to the 6th. So we've got a bunch of these that are zeros, so those aren't going to do anything. This should be the 3 zeros. So we really only have to add 1 times 1, 1 times 4, 1 times 8, and I don't know what 2 to the 6th is. Let's see. 2, whoops, I'm in the wrong part of my calculator. 2 to the 6th, 64. Okay. Plus 1 times 64, well, which is just 64. I don't know why I didn't write the 1 times on any of the others. I don't know why I wrote it on that one. So 64, 8, 4, 1, 77. So 77 is the base 10 equivalent of 1001101 base 2. So that's what the process would look like. What if we wanted to code that in Python? So one thing we could do is we could just hard code in this, right? We could do the math in Python. I don't know why you'd ever do that, but let's show how you would do that if that's what you wanted to do. So let's just say that, oh, I need to show you what I'm doing. Let's make sure that you can see. There we go. All right. So in the decimal equivalent equals, and we're going to put this equation, it's not going to be on your screen right now. The equation's not, but you should be able to see what we're writing in Python. So what we had was that whole big summation, right? So the first thing was 1, and then if you want to do multiply, I assume you know how to do multiply. So times is just shift and 8, the asterisk, or the asterisk key over on the number pad or whatever. 2, and then to raise a power, a lot of people are going to make a mistake here, and they're going to do the little caret, because a lot of times in other languages, that's how you do the exponent. But for Python, it's actually 2 asterisks. So asterisk, asterisk to get to this. This number that we have on the screen now would say 1 times 2 raised to the power of 0. And then if we want to do the rest of it, let's go ahead and type the rest of it in. 1, or next digit was actually 0. Let's space them out so that they're easier to distinguish. 0 times whatever, but it would be 2 to the first. And then we had a 1 times 2 squared. And then we had a 1 times 2 to the third. Then we had a 0 to the fourth times 2 to the fourth. Then we had another 0. And then we had a 1 times 2 to the 6th. So that's what we just did by hand. Print in, we have to put what we want to print inside these parentheses, right? So we don't just write print in. Now actually, if for some reason you're in an older version of Python, like a 2 point whatever version, then the print function is different. But I'm assuming that most of you are running some 3 point something version of Python, in which case you have to put what you want to print inside the parentheses. It does not print the letter in. If I wanted to print the letter in, I would need to put the whatever the letter in this case, between quotation marks. But if I want to print the value of in, then I just put in. So let's see if this actually gives us our 77. It should, oh, I have to save it. Let's save it to the desktop. All right. Oh. Why did I get a, oh, Python is a particular language, and I put a capital P, so let's put a lowercase p. Notice it turned purple, and they're down here in our shell output. Assuming you're in Thonny, you have some kind of shell that you can see. If you're using idle or something else, it'll show up somewhere else. But there's our 77. Now, this is not how you would ever actually do it. You just wouldn't do that. Anytime you have a repeating pattern like this, something times 2 to the something, and the 1, 2, 3, 4, you would make some kind of loop. You wouldn't just do this by hand over and over. That would be a little ridiculous. What if you had 1,000 digits or whatever? It would make no sense to do this by hand. I want you to see two things. One is the what's going on behind the scenes. Plus, I want you to see the using the 2 asterisks to do a exponent in Python, because that is something that gets overlooked a lot. We could do a similar thing for hexadecimal. The difference with hexadecimal, and I'm not going to work it out, but the difference would be that you do have letters in there, right? Like A through F. So where's our sheet with hexadecimal? You have these letters A through F. So if you put a letter into this an equation like this, you would have 16 instead of 2 here. Then it's not going to really make any sense. So if you're doing something like this with hexadecimal, instead of A, you put in the number 10, B, you put in 11, 12, and so forth. So that you actually have numbers in this equation. So you don't leave them as letters if you're converting hexadecimal over to decimal. You put in the decimal equivalent of A, B. Wow. I don't even know what I wrote here. A, B. I wrote an E. Obviously, this should be A, B, C, D, E, F. Not sure what I wrote there. I just now noticed that. All right. So I'm not going to go through a hexadecimal conversion. I think it would look the same, except that you would have 16s in here instead of 2s. And maybe you'd have a different number of digits, possibly. The number of digits that you have is just dependent on how long this set of digits happens to be. There are some standard sizes, like a lot of times 8 of these would be a standard size because 8 bits is a byte. Sometimes 16, that's a word. 4 is a nib. And so there's different standard lengths of bits strung together in a computing system, but there doesn't have to be. There just are some standards. Let's see, what else might we want to do? Also Python, I believe, does have the systems, or at least the common systems, built into it, and you can convert between them with just a single line. You don't have to spell out everything like we did over here. But we'll get to that at some point when we need it. Right now, we're trying to learn about how the systems work. So the other thing we might want to do is go from decimal to one of these systems. This process is really straightforward. It's not even really an equation for it. Basically you just divide. So the difference is you continually divide until you have a quotient of 0. So you have to remember the quotient and the remainder and what all those things mean. So let's go through an example by hand of converting the number 134 base 10. Actually, that's just too small of a thing. 134 base 10. We're going to convert that over to binary. So we want to get it into base 2. And so how you do this is you continually divide, in this case 134, you divide it by whatever your base is. So if your base 2, you divide it by 2. If your base 16 hexadecimal, you divide it by 16. So 134 divided by 2 is 67, and the remainder is 0. So we need to keep track of the quotient and the remainder. The remainder is actually going to produce the the binary number that we're trying to create. The quotient will tell us when we've actually done all of the division we need to do. So whenever the quotient, so this guy's the quotient, and this one's going to be the remainder. So whenever the quotient is equal to 0, that means we have done all of the dividing we can do. And if the remainder, we just keep track of it. So the remainder might equal 0 sometimes along the way. Right now it equals 0, but that doesn't mean to stop. We couldn't say that the binary equivalent of 134 is 67. That doesn't make any sense. It's also not 0, so we have to keep going. We keep dividing by the base, in this case 2. So we want to convert to binary until the quotient is 0. So, and so next time we'll take the 67, divide it by 2. So 67 divided by 2 is 33, so you could get to 66, right? You'd have a remainder of 1. We don't stop here because our quotient isn't 0. So we take 33, divide by 2, and we get 16. You could get to 32. You'd have a remainder of 1 again. We take the 16 over, divide it by 2. You have 8, remainder 0. The 8 divided by 2. So you have 4, remainder 0. But the quotient isn't 0 yet, so we're still carrying on. So the 4 divided by 2 is 2, remainder 0. The 2 divided by 2, so that's just 1. Remainder 2 divided by 2 is 1, remainder 0. Now I get to 1 divided by 2. So 1 is smaller than 2. So I finally have a quotient of 0 and a remainder of 1. And this string of numbers over on the right-hand column, that is the conversion. I was trying to look for something to highlight with, but we'll use this. So this is the column of numbers that would be the binary equivalent of the decimal number 134. I have to know which order to put them in, right? Is this number 0110001 or is it 100001110? And it turns out that you would need to convert these where this is the most significant bit and this is the least significant bit. So the binary number would be 10000, so 10000, 110. 1, 2, 3, 4. Yeah, I got enough zeros in there. Base 2, so this is binary. So 134 base 10 equals this number, 4 zeros, 110, in binary. Again, not a thing that you're going to necessarily have to do often, convert from one, other than like in an academic setting where there's an exam and your question is asking you convert this number to this base. Now, we probably wouldn't ask a one that a calculator could just do. It probably would be a made-up system. So convert 134 base 10 to base 4, something like that, that you don't actually have built in. If you were doing that, if you were trying to do 134 base 10 to base 4, what happens is all of these 2's here turn into 4's. So you divide by 4 over and over until you get to a quotient of 0, and then you have a set of remainders that you could deal with. Let us use this process to build a Python program to do this. Now, again, this is already built in. There are already functions that do this conversion, but I actually want to use this more on how to code some stuff so that when we need to code a variety of different things, we have some idea how to do it. so let's go back to Thani, and we don't need this part. Let's erase this. We are going to need a couple of new functions, and so we need to import a library. It's not the plotting library that we installed last time. It's just math. So it's just import math. And you shouldn't have to install math. Math should be one. I didn't even check, but it should be one that is already in here. Well, it's not going to be a separate library. It should be just built into Python, the base package of Python. So you don't have to go install math. But what this does is it's not like letting us add and subtract. It's letting us do things like the floor function, which we'll talk about in a minute. All right, so let's say that we have a decimal number. We'll use the same variables, or at least as many of the same variables that we had before now. So n, capital N, will be our decimal number. And let's just make up a number for that. So here's our decimal number. We could, I don't think I ever did this where you use a pound symbol, hashtag, octothorpe, whatever you want to call it, as a comment. So see how it's all kind of light gray in this editor? That's telling me that this is just a comment, that it's only going to be read by humans. It's not going to take up any computing space or power. And so you can make comments in line with text, or well, with code, with this pound symbol, hashtag symbol. Let's go to base 16. So our base is going to equal 16. So, oh, I didn't want to do that. There we go. So we could put any number we want to here. Again, a lot of these things like this 74, 754, 16, they could be hard-coded into what we're going to write for our code. But it is usually better to put as many things as possible into variables, so that if I ever wanted to change this into a different conversion, I wanted to change it to a base 8 or whatever, I just have to change one thing, not every instance of that variable in my code. All right, so let's set our index to equal 0. So this is the index in the summation symbol. Oh, we need to create two other things. Q is going to equal, now this may seem odd, but it's just two brackets, the open bracket and closed bracket. So if you remember from last time, the brackets represent lists. Now there's nothing in this list, so this is going to be an empty list for the quotients. And we'll need a similar one. We'll use R. And that will be an empty list for the remainders. So we have to start them out as something. They need a place when we want to store Q or R. You know, we want to store all of these numbers. We don't really need to. Well, we do need to store the quotients because we have to divide by them the next time, and we need the remainders. So we have to store them somewhere, and we're going to store them in a list. So we just created an empty list to start with because we don't know what they are ahead of time. All right, so now we started our index at 0. Now the first time we're going to run this thing, or code this thing rather, is we're going to do it just the way we did on paper. So we're going to basically work out the steps by hand on paper, and then we'll figure out, all right, well, we do have a computing system here that can do loops of things. So how can we make this work in a loop? So here's the first way. So the quotient, the very first time, is we need to divide our number, in this case n, divided by our base, which is b, and we're going to get a quotient and a remainder. So Q, now Q is the name of this empty list. So what I want to do is I want to what's called append. So append means add a piece of data to the end of a list. So right now the list is empty, so it's going to be actually the beginning, but it's the only one in the list at all. So it's going to put a piece of data at the end of this list Q. And that data that I want is, I want to do some special math. I want to use what's called the floor function of my number I'm converting in divided by the base system I'm converting to. So we got to talk about well, math is just that it's a function built into this library we imported. Floor, you might not have heard before, but there's a floor and a ceiling, and if you don't use either one of those, that's the math that you would know on your just regular math. So what the floor does is it takes does the division in divided by b, so 74754 divided by 16. It does that division, but it rounds it down. So no matter what number, floating point number, so however many decimal points there are at the end of it, it's going to round it down. So let's just look and see what calculator went off. 74754 divided by 16 is this number, 4,672.125. When I do the floor of this division, I just get 4,672. And it throws away all the decimals, no matter what the decimals are. And the floor means it's automatically going to round down. If I put in ceiling, then it would automatically round this up to 4673, even though the decimal is only 0.125. Ceiling rounds up every time. Sometimes there's a reason you might want to do that. So this is floor, so it's going to give me the quotient, and that's what I put. I put that number, 4,672, in the first spot in this quotient list. But I don't have a remainder. So remainder, so R is what I have for the remainder list, is going to be the same type of thing. I want to append a value to it. This one has a function in, I'm going to use the percent sign here, but this percent sign means modulus. So what it does is it is going to take only the remainder part, so the 0.125 or whatever it was. It's going to take just the remainder and put it in the list R. So the little percent sign is just the remainder. All right. So if I ran this, I would have a one value in Q and one value in R. All right. So the next time, so again, we're hard coding this the long way. We're not doing it the actual efficient way. So let's go to copy this and paste it. Now the index is increased by 1. So we could just say that I equals 1, right? We could just do that. We're not going to do quite that level of hard coding. We are going to say that the index is plus equal to 1. So, well, I got an extra equal sign in there. Plus equal to 1. So what this does is this I plus equals 1, that's the same thing as, let's do it as a comment. I equals I plus 1. That's the same thing. It's a slightly shorter way of writing I equals I plus 1. So you put the plus and equals together. You can do the same thing with minus equals or divide equals or whatever. But you'll see this plus equals 1 often when you just want to increment a value by 1, or plus equals 2, so you want to increase it by 2 or whatever. But it's the same thing as I equals I plus 1. So you're just going to add 1 to the value. I do want this part again. I want to add a new value to the end of my list Q. So I want to keep that. But now I don't want to add, do the dividing of N divided by B. I want to divide, and here is where I'm going to use that list of quotients. I want to divide Q. So the thing that I just had before, the 4,672, but I don't want just any Q. I want a specific one. I want the one that's immediately before where I am now in the division. So where's my sheet of paper go? So see how I take this quotient and it's the one that I'm doing the division on in the next step. So if I think of, right in this first part, I'm at I equals 0, I equals 1, I equals 2. The number, the quotient I want to divide by in the I equals 1 step was the quotient of the I equals 0 step. So I could write that as I minus 1. So what I've done here in this little piece is I've taken the, I'm not appending this value, I'm going to go and take this value, Q brackets I minus 1 would be the same thing as writing, I want Q0. So Q0 is the value in the 0 position. So remember, these lists start counting with the first position is the 0 position. So it would go take whatever is in the first spot of this list. Right now there's only one number in there, the number that we put in there in this step. So that 4,706 or 4,672, and I will go and take it and do the math on it. Same thing here. I don't want to use the create the remainder from n. I want to create the remainder from I minus 1. Whoops, got to be a bracket, not a brace. That should work. And now I've got 2 numbers in my list for Q and 2 numbers in the list for R. Now the part I'm going to cheat at is that I know how many times I need to divide this. So we need to do 5 of these for it to work out. All of these are the same though. I increase I by 1. I take the previous value in the quotient, whatever it is, and I do that twice. I do it once to create the new quotient and once to create the new remainder, and I do that a couple more times. That 1, 2, 3, 4, 5. That's all I need. So I would have to know in this particular case. I don't know what the quotients are. I guess I could have a little check that we'll have in a minute to figure out when I have a quotient of 0 that I'm done. But now all I need to do is print. Oh, I did it again. Lowercase p, print Q, and print R. So when I print these, it's going to print all of the numbers that are in the Q list and all the numbers that are in the R list. Remember though, also back over here, that it put the numbers in the, remember I want the remainders, right? It put them in this order, but I actually want to read them out in this order. So this one being the most significant bit, this one being the least significant bit. I want to put them, or I want to read them out the other way. So to actually do that, there is a command, just like there's this append command and floor command, there's a reverse command. These are list commands here. Append and reverse are list commands. So I can reverse my list. So it takes whatever is stored in R and it switches them backwards. It puts the last thing in the first spot, first thing in the last spot, and it flips all the in-between ones. It makes a mirror image of the list. It reverses it. And then I can print R and I will get the actual thing. So let's run that. All right, so down here, there's the initial quotients. Here are the remainders, and this is the remainder list after it's been reversed. Donnie, oh, okay, sorry. I just ran it and I got this little block of code. I think you saw, oh, maybe you didn't see this part. Reverse is the command I used, r.reverse. So this list is Q, print Q, and it was created with all these Q, append, do some math with the floor math. All of those are put into this list. This list is print R right here. So it's all the remainders. So it was created by this command and this math and this math and this one and this one. And it's the remainders I want to be able to use to create the new number, base 16. So I had to reverse the list R, and then I printed it again. So that's why these two are just the same list but reversed. All right. It would be nice. Let's add one more thing. So the main point of this is not to do this math. It's to see commands like append and reverse and floor and things like that. Here's another command. So this is technically the number I want 12,402, but it's in a list. So I want to print it out as the number 12,402. So let's create the number. And one way we can do that is we can create a new variable s and put all of those numbers 1, 2, 4, 0, and 2 from the list r that we've reversed into this variable s. So we can't just put them, we can't just say s equals r0 plus r1. We can't do that because it would actually add them up. So it would just add 1 plus 2 plus 4 plus 0 plus 2. So what we have to do is we want to add them, we want to concatenate them, not just add them. So we want to keep them as basically characters, not numbers. So we're going to say this str. So what this does is it takes the number in the R0 spot, so 1 right here, and it takes the string representation of that number, not the numeric representation of that number. So it just takes the character 1. And then we're going to add that to the string R in position 1. Again, we're doing the same thing over and over again, 0, 1, 2, 3, 4. So this would be a good place for a loop, but right now we're going to do it the hard way. Let's see, we got a couple more of these to do. All right, so that should do it. And then we need to print this out. Except I used a capital S, didn't I? All right, so let's run it again. And there is the actual number that we were trying to get. So we were trying to convert 74,754 to base 16. We did all of this math, did this little process to string all the numbers together, and then we printed it out, and we got this 12,402, but that's in base 16. All right. I did want to show how, since we did a lot of things like I literally cut and pasted this line 4 times, anytime you can cut and paste something and just paste the exact same thing over and over again, that tells you that there's probably a better way to code this. I probably could do this in a loop, not in a cut and paste. So let's actually get rid of these, so that these are the ones we cut and paste. So let's get rid of those. Oops, and I left, I don't know where that came from. All right, so let's keep this where we assign our initial value for the decimal number and the base we want to work in. Let's keep those. We still need math. Let's keep our empty list Q and R. And we still need to do this one. This one I did cut and paste it, but I had to change it after I cut and pasted. This is the first one, so we get started with this one. So let's keep that one. And let's keep all of this where it creates the list and reverses it, or not creates it, but it prints them out and reverses them. We could go in and automate this part also, where we create the final number. We'll not do that today though, because it's taking a while to do all this. Let's create all of that little part in the middle where it just does the dividing over and over again. So you might know that our idea was you keep dividing until you get a quotient of 0. So I'm just going to keep running through a loop until a certain thing happens. So that means it's a conditional loop. And in this case, I'm going to create the condition by saying that while Q of whatever index I'm currently on does not equal, and so you does not equal with an exclamation mark and equal. That does not equal 0. So as long as the quotient is not 0, then keep going. As soon as I get a quotient of 0, then don't do the loop anymore. Do whatever's after the loop. I'm going to put an R on here. Ri is greater than some big number, so that maybe there's some giant number that I don't want it to just sit there forever. So it does time out eventually. All right. So while certain things are happening, I need to. I shouldn't have erased all of our commands, but one of the things I had was I plus equals 1. So I did have to increase the index. So I started it with the index of 0 up here, and then now it's going to be 1, and the next time it runs through the loop it'll be 2, and so forth. And then let's do our math. I guess I should have left this in there too so I could just paste it, but let's type it again. Append, we're going to add to the end of our list. Math, and we want the floor value. We're creating the quotients right now, so we want to round down. And this is exactly what we had before, right? Q of I minus 1 divided by B is what we had. So divide by the base. And another parentheses. Okay. That will put a new value at the end of the list Q. We also needed to keep track of the remainders, so we did that with R. We appended a value to the end of that list, and it was the Q, capital Q, I minus 1. So the previous value for the quotient, and we did a mod B on that. So that's only going to give us just the remainder. So the first line creates the quotient, second line creates only the remainder, and we put them at the end, append, so we put them at the end of the list here. That should be all that we need to do, except that, well, yeah, that should be exactly all we need to do. So let's run that. And there's our same results that we had before. But now you could start to see that other than this part is kind of hard-coded in to where it's expecting a 5-digit number in the result. We could do a similar thing here to create the string as we go. We could actually create the string inside of here as we go if we wanted to, so that we don't have to create the string later, except we couldn't, could we? Because we have to wait until the end, because we have to reverse it. So maybe we would want to do a little loop out here to create the string representation of any length of number right now. But we could change this to some other thing. It'll probably give us a little error. Yeah, see, it gives us an error because we have this hard-coded in that it needs a fourth one. And there we go, or a fifth one or whatever. So right now we don't have a fully automated converter because of this part being hard-coded in still. But we do have the idea that we can create lists. Now, it did do some weirdness down here. It spit out 5 digits even though I only have 4. So there's some debugging that we would have to do to make this thing work correctly. We'd have to go in and track down why it spit out an extra digit. But this is what I wanted to show you is the while loop in here. So it knows when to end the while loop, Python does. It's sort of like a for next type loop. It's a conditional loop, except there's no end. You know, it doesn't show you where to end it. Python uses the idea that if you give it a condition like while, then all the lines that are indented at that level underneath it, see how I indented them all? I'd hit tab. They are the lines that will continue to repeat. They're the lines in the loop. One of our digits is one of our digits is 10. That's why it did a weird thing down here. Good catch. Yeah, I see it now. All right. So this is a tricky part of Python. Is I indented these lines. And sometimes you will go in and now notice when I hit enter, it just automatically indents it. But if I'm coming back and editing it or whatever, I can add spaces to get over to the same amount and do something. And there's a chance always when you mix the idea of spaces and tabs that Python won't like that. I don't know if Thani is good about catching that or not. Well, it actually did. It did it okay. But some editors will not like the idea of mixing spaces and tabs together in Python. So if you ever get these weird errors and you can't track down what's going on, but you cannot find a problem in your code, if you have anything that are indented, there's a chance that you mixed tabs and spaces, and it doesn't like that. Thani seems to be okay with mixing tabs and spaces. Let's see what it does if I... Yeah, so see, they're not indented the same amount, and I get an error. So there can be little picky things like that in Python that will sometimes drive you crazy. As long as they're indented, at least in Thani, as long as they are the same level of indentation, it's okay. But as soon as there's something not on the same level, it's going to give you an error. All right, so the main things I wanted you to get from that were the new math functions. So the floor function, modulus probably isn't one of the math functions. That's just a built-in function. Append, reverse, so some of the things you can do with lists. Some of the coding type things. So while loop, how you might use a while loop. This is not going to work. There we go. Some things like that. It's not necessarily the idea of manually going in and converting between decimal and hexadecimal. Obviously, there are much simpler ways to do that than what we will do with this code here. But it is good to know how the conversions are happening so that you can create new conversions if you need them, or you can track down an error, or you just have an idea of how the numbering systems relate to each other. All right, let's leave coding for a little bit and let's go look at our gauge blocks. So, well, let's mention the idea of standards first. So there are 7 standards, primary standards. Time, so there's a way to measure time that is the standard second. Mass is one of them, so the standard kilogram. That one is like last year, maybe it was 2 years ago, last year. It was very recently that it was finally updated to be something that wouldn't be changeable. Until then, there was a literal hunk of metal in France that was the prototype standard kilogram, and there was some evidence that it was changing weight over time. There were copies of it made, I don't know how many 100 years ago or whatever, and they didn't all weigh the same amount anymore. So somehow there was some discrepancy between the prototype and they were called the sisters, and they needed a way to quantify or establish the kilogram, and so it's been the most recent one to be reestablished. So time, mass, the amount of a substance, so moles, luminous intensity, so how bright is something, so how do you quantify that, temperature, current, so current in a electric circuit, and length, so a distance. So those 7 things, any other thing that you're going to calculate or measure can be composed of those 7 quantities. And those are the primary standards, and they're all based on things that shouldn't change anymore. They're based on universal constants. So unless for some reason the universe changes, the universal constants should stay the same. Originally they weren't created that way. They were the kilogram was a piece of metal, a literal piece of metal that they just tried to keep in a vacuum and didn't let it rust or anything, and that was what a kilogram equaled. Time was based on maybe the rotation of the Earth, but even that doesn't stay constant. It's gradually slowing down. And now most of these deviations we're talking about are extremely small deviations, but they make big differences depending on the scale that you're operating at. My favorite one was current. It was actually, current is talking about electrons flowing through a circuit or a wire. It was actually measured until relatively recently as a force. So it was the force between 2 wires that had a 1 amp current would create a certain amount of force between the 2 wires, like magnetic force between them. And they've all been converted over to things that are hopefully not going to change. They're constant. I've got a document on Moodle that goes through all of the actual equations, and there's a lot of interesting things about each one, and you can look them up. They're on Wikipedia and everywhere. But just know that there are these constants, and there are institutions that quantify them and can validate them. And then you get things like, you can have, now this is not a super expensive set of gauge blocks. This is the low end of gauge blocks, but you can get something like this. So if you want to measure length or a distance, then there are things like this. Obviously you have, rulers and calipers and micrometers and things like that. But this, obviously, for one thing, the ruler doesn't have very many divisions on it. But this ruler didn't come with any kind of certification of how accurate it is. It just, I just have to assume that, well, whoever printed this is more or less going to be correct. Shop Fox, their printing process worked that day. But when you get a little bit higher end, now again, this is not super high end. This is still lower high end. When you get something like this, you get a certificate of calibration and traceability. So this gives you a, what grade are these? So AS2, that's not the absolute lowest grade. There is a grade B, but it is pretty low grade for something like this. It tells you that these are made of steel. Gauge blocks, when we look at it, I guess we can see them. They're literal blocks of material. So they're either usually steel, these are steel, or they're ceramic. There might be some other materials, but those are the two materials that they seem to mostly be. It tells you what standard. So there's an ASME standard for gauge block calibration and gauge block tolerance and everything. And it says what standard they're trying to meet. And it shows the actual test number where this set of blocks was tested against that standard. And then this chart shows you, now the gauge blocks, these are metal gauge blocks. I'm going to use some gloves to touch them, just because oils from your skin can cause them to rust and everything. But this block, for instance, is 0.1. I don't know if y'all will be able to see the tiny details on here, but it's etched into this front surface. There it is, 0.18. That means across these two flats is 0.18. These are inch series, so this is 0.18 inches. But it also has its own serial number. You can kind of see it there at the bottom, right in there. And on this chart, if I go to the 0.18, HO538, there it is. It's telling me it's +3 out of what it's supposed to be. Now this +3 is +3 millionths of an inch. So these things, even the cheap ones, the low grade, the grade B, which is below these, are out by no more than 50 millionths of an inch. Now I noticed on my sheet here that I do have two, the 0.19 and the 0.4, that are a good bit out. They're out, this one's 30 millionths over and that one's 38 millionths under. So those two, they don't actually, as far as the way I read the AS2 standard, which we can look at, I think I still have it pulled up. Let's see. Well, let me show you these. So here is the standard itself. So if you wanted to go get the standard from ASME, a lot of these standards, ASME, NIST, there's a lot of different standards. This one is just the standard for gauge blocks. And you either, $40 for it. It's probably not even that many pages. We have a preview. Let's see what the preview shows. Let's see what's in the preview. I actually get 15 pages of preview. So, there are square gauge blocks. Gauge blocks have actually been around for like over 100 years, so they're not a new thing. They're an older thing. They were invented over in Sweden. Actually, I have the Swedish style with the rectangular blocks, but there are some that are square blocks with a hole in the middle. And so this is what a standard looks like, and it shows you the sizes that you might find in a set. I do not have a full set, but I have a pretty full set of them over here. And so you can see all of the things. There's the deviation in flatness and how you're going to measure. a wringing test. I'll show you about wringing. Wringing is the coolest thing about the gauge blocks to me, and that's kind of what the original patent was for. Not necessarily the wringing, but for the sizes that are available to create all these different sizes. But it has to do with wringing. And that's all we get. We get those 15 or pages. Most of them are just intro material. All right, so the standard, let's see, here's one. This is from Michitoyo. So they're a measurement metrology company, basically. They make lots of different tools for measuring things. And so they make gauge blocks. My gauge blocks are not from them. They're from, I don't know, HFS, Hardware Factory Store. So not really the same quality. But here's grade 2. So it'll show, I have gauge blocks up to 4 inches in width. So I could go, up to here. And it'll show that they're supposed to be, for grade 2, within 14 millionths of an inch in their tolerance. They make them up to 40 inches long. That's like a meter. And they're still only out 40 millionths of an inch over something a meter long. So they're really made very specific. And just even handling them incorrectly can cause them to have problems. So what you do with them is you'll notice there's a lot of different sizes here. And you can go in and stack them together. But you don't just stack them together, you ring them together. So basically, take something, a light oil like WD-40. Just going to spray some on this thing. There are some other processes, like my gauge blocks could probably benefit from being flattened a little more. In fact, you can kind of see, or I can see, I don't know how well you can see, that this surface should be really polished. And so should this one, but I can definitely see the scratches on it. But you clean them a little bit on each side, particularly the side that you want to ring together. So I've got a 0.15, and let's get a 0.18. Was that the really bad one? No, it's actually really pretty good. So I'm just cleaning the side. Sometimes you take a stone, like a whetstone type thing for sharpening a knife, but it has to be super flat, and you can run them across that to make sure there's no burrs on them. These I haven't used very much, so they shouldn't have any kind of burrs. You don't want to ring a bird, it's got a dent or a spot that's poking out. You don't want to ring that with another one. So what you do, there's a couple of different ways to ring. And again, these won't ring super well because they're pretty cheap compared to normal gauge blocks. But you take and you press them down. Now, I'm actually having to push pretty hard, and you slide them together. It's working. All right. And now these are essentially one block. And they will stick together. They have a decent amount of force of how, I don't have a glove on the other hand, so I don't want to pull on them, but they're pretty much stuck together as one block that is now 0.18 plus 0.105 thick. So if you can create, with your whole set, you can create a variety of specific lengths that are within millionths of an inch of what you intend for it to be. So you can use them in machining. You can use them to calibrate other tools or whatever. You don't want to leave them stuck together very long because they can become hard to take apart. But typically you twist them and they'll slide apart. So there they go, come apart. So they're really cool. And now you have a way to go in and, you have a standard that these things, let's see, we certified that the accuracy of these gauge blocks, it's got a big book. Let's see if we can take that out of the bag so that it's not reflecting. Accuracy of the gauge blocks has been determined by comparison to master standards, which are directly traceable to the National Institute of Standards and Technology of the United States of America, blah, blah, blah. So there are these labs across the world that hold primary standards. So they have gone through the standard procedure, whatever it might be, for creating, in this case, a length standard, and they have the absolute meter or whatever it is that they have created. And off of those at the labs, master standards have been created. And in this case, maybe this company has a master standard when they're making these gauge blocks, or maybe they source it out to someone who does have a master standard. And so that master standard is compared directly to one of the primary standards and shown to that, yes, this matches within reason. And within reason might be a millionth of an inch or whatever, I don't know. But you have a trace, and even on the box, it even says, I think, well, it sort of says, this, if this was all spelled out, this word would be traceable certificate, so that there's an actual test that I can trace back to. So I can go and, if I really needed to, I could trace it back to this test. This person's name, I don't know if that's an actual signature or a printed signature, but that person was in charge of running this test and producing these results for these individual gauge blocks. There's a serial number. Now, I haven't ever bought two of these sets from this particular company and checked to see if every one of these has their own serial number. Like if this is the only J0824 out there, or if this company takes a little shortcut and just the .05 is called that. But it should be that that's the only one out there. And then that particular one was tested and shown to be plus 8 millionths of an inch out of whatever it's supposed to measure to 0.05 inches. So a lot of tools, higher end tools, have that kind of certificate. And they are traceable to one of these standards somewhere. And someone has actually gone in and compared your tool to a secondary standard or a master standard or whatever standard they've I did go with English units. The English is interesting. We do a lot, English units and metric units. Most English units are actually based now on their metric equivalent. So they are like the inch is actually not defined in anything other than 25.4 millimeters. So they're defined as versions of the metric system. And I did go, this set is a inch set, just because whenever I would use this, I would mostly be using equipment like a milling machine that is set up for inches or whatever. So it's more convenient for me. And again, this is not a super high-end set. If I were buying like one of the multi-$1,000 sets, I probably would go with the metric set, or the SI set, the System International set, instead of the English set. Let's see. I think, well, the only other thing we were going to talk about is character encodings. I think I'll actually save that. That one's not it's talking about ASCII and Unicode. Basically, we have all these numbers now, like the binary numbers that we can deal with. How do we make those numbers represent letters and things like that? I think we'll do that next time, just because it's not going to add a whole lot for today. So I think we'll call it a day. And next time, we'll do the character sets. And what else we're going to do? Some soldering. I think we have to do some soldering. Homework 1 is due Tuesday, yes. So Tuesday morning is when I have the actual due date. But you turn it in on class 2, I think is where the turn-in spot is. Yes, it's on class 2. We'll also do some database operations in Python. So now that we have these list ideas, how do we actually do more interesting things? All right, I think that's what we'll head out to. Next week, also, Thursday, we won't have anything. I'll just remind you of that now. That's, for those of you on campus, well, actually, you don't have to be on campus. It's virtual. So the career fair is on Thursday. So we won't actually have class of any sort on Thursday. All right. I think we're good for today.